Okay, so welcome back, and we're now going to talk about the period of a pendulum. Okay, so what is the period of a pendulum? So I drew this diagram here. So what this shows is a pendulum. So it's a weight suspended by a rod. So the rod is attached by a swivel of some sort. And so when you pull the pendulum to a certain angle, let's say theta, which we're going to say is the maximum angle that it takes. So we pull it out, and then just using gravity, we let go of it and let the force of gravity pull it back. The period of the pendulum is the amount of time it takes to go one full swing, assuming that it comes back to its original position. Okay, so it takes this full swing, comes back. The amount of time that it takes for it to do one full swing back and forth is the period. We represent the period by capital T, and it's given by this formula, this integral. Okay, so what we're going to do is we're going to estimate the period of a pendulum. Oh, by the way, it also depends on the length of the rod, right? So that's L. So we've got period, the theta, which is the angle with which the pendulum makes with its equilibrium position. So we've got this equilibrium position, which is straight up and down when it's at rest. Okay, and then when a force is applied to the pendulum, then it starts to swing, and again, disregarding air resistance. The angle that it makes is going to be theta, which is the angle that the position of the pendulum makes with the equilibrium position. So it's going to go out to theta max here, or negative theta max here. Okay, assuming that this is like an x, like negative angle versus a positive angle versus negative angle. And then the length of the rod that's attached to the weight is given by the capital letter L. And so that's what we're using in here. Now, in this case, we're going to use the binomial series because it fits that form. Okay, where in this case here, this is going to be our 1 plus negative k squared times sine squared theta. Okay, so where this is going to replace x. So 1 over the square root of 1 plus x, where x is going to be this negative k squared times sine squared theta. Oh, and by the way, k equals sine of theta max divided by 2. Okay, so that's the constant. Okay, now, putting this in for the binomial series, right? So now we're going to replace that, and what do we get? We get the following. We get the integral from 0 to pi over 2 of what? Well, our series becomes 1 plus 1/2 k squared sine squared theta plus 1 times 3 over 2 factorial times 2 squared times k to the 4th times sine to the 4th power of theta, and then it keeps going. D theta. Okay. So now now the first part of this question, they say use the first term of the integral. It says use only the first term of the binomial series to estimate the period. So we want to estimate the period of the pendulum given this scenario, but we want to estimate it just using the first term. Well, the first term here is just 1. So if we want to estimate just with the first term, we're just going to have 4 times the square root of L over G from 0 to pi over 2 of d theta. And of course, this is just going to equal then 2 pi times the square root of L divided by G. Why? Because we're integrating this from 0 to pi over 2, which is just going to give us theta. And the evaluation of that from 0 to 2 pi is just going to, or excuse me, 0 to pi over 2 is just going to give us pi over 2. And so pi over 2 times 4 gives us 2 pi. And so we get this. So this is our estimate. Now, the thing is if k is small, or excuse me, if theta max is small, so looking at this here, so if theta max is small, then k is going to be small. Okay? So we can claim that when k is small, then this is going to be a good estimate. And so to justify that, we're going to look at just this integral here. Okay, so we're going to justify that by just looking at this integral. Okay, so let's do the integral from 0 to pi over 2, and it's going to be of 1 plus 1/2 1/2 k squared sine squared theta plus 1 times 3 over 2 squared times 2 factorial times k to the 4th sine to the 4th theta, and so on. Okay, now, so, d theta. Okay, so now, if we have that, and let me get rid of this here. Okay, so if we have this, well, since sine, right, the absolute value of sine theta is less than or equal to 1, then we know that this is going to be bounded by what? It's going to be bounded by this. And so sine theta is going to be 1, right? So we're going to make this the maximum it can be, which is when sine is 1. So that means all of these are just going to be replaced with 1. So our, and we know that then we're going to get 1 plus 1/2 k. This is going to be bounded above by this. Okay, which, by the way, is less than oh, yeah. So now if we integrate this, we know that this is going to be less than 1 pi over 2, right? Because we're evaluating this. Okay, and so if we integrate this, well, all of these are constants, right? So if we integrate this, we're just going to get theta. And so if we integrate this, theta is just going to be evaluated at pi over 2. So this is going to be less than pi divided by 2 times 1/2 k squared plus 1 times 3 over divided by 2 squared divided by 2 factorial, k to the 4th, plus, and so on. Okay. Now, it can be shown that each coefficient on the right-hand side, or above here, or excuse me, here, all the coefficients on this is less than 1. Right? So it can be shown that all of these coefficients are less than 1. Okay? And so what happens? Well, if that's true, if all of these are less than 1, well then that means that this is going to be less than what? Well, we're just going to replace these all with 1. And so this becomes pi over 2 times, what do we get? Right. Oh, hold on. There should be a 1 here. 1 plus, and k squared plus k to the 4th, and so on. Or no. I'm sorry, no, we're not doing, yeah, I'm sorry, we took out the 1 here. This is 1, so no, I had it right the first time. This, oh yeah, no, that's right, okay. So now, since these are all less than 1, we're gonna factor, this becomes, hold on. Let me do it in a couple of steps here. So this is going to become k squared plus k to the 4th plus k to the 6th plus, and so on. That's what I want, okay? So now we're going to factor out k squared. And so by doing that, this is going to equal pi times k squared over 2 times 1 plus k squared plus k to the 4th, and so on. And then, of course, this can be written as a familiar formula that we've seen before, because that is a geometric series. And so now we can write this as pi times k squared over 2 times 1 over 1 minus k squared. Which is small for k being small. Now, for larger values of theta max, we can approximate t by using more terms of the integral. So if k is small, then using the first term of the integral is sufficient. But if we have larger theta, what if we have a larger angle? Okay, then it's going to require more terms to get a better accuracy. Okay, so in part B, we use more terms. So in part B, they want to use the first 2 terms. Okay, so if we have a larger angle, then the first, well, in this case, they want us to just use the first 2 terms. So if we use the first two terms, we get the integral from 0 to pi over 2, and it's going to be 4 times the square root of L over G. And in this case, the first two terms is going to be 1 plus 1/2 k squared sine squared theta d theta. Okay? So that's the first two terms. And so if we integrate that, right? So in other words, t is now going to be approximated by that. And if we integrate that, we end up with 2 pi times the square root of L over G times 1 plus k squared over 4. And that's it. Have a great day.